All right, now for the second set of lecture slides for Chapter 9, we're still talking about stress transformation, but now we're getting into the principal stresses and maximum in-plane shear stress. So I talked a little bit about it in the previous set of slides. The purpose of this section is to develop equations to find what our maximum stresses are and to find at what angle with respect to our typical XYZ axes that we set up when we're doing, for instance, combined loading problems, that those maximum stresses are going to occur at. So I mentioned before that this concrete, it's a brittle material, and brittle materials tend to fail in tension. So the bending that was caused by this experimental setup caused tensile normal stresses to develop at this angle, and that's where it failed first. Similarly, for this chalk, it's also another well-known brittle material. If you were to take this chalk and twist it, so apply a torque, therefore induce torsional shear stress on our cross-section, our typical cut through our cross-section like we did in Chapter 5, and the tensile normal stress that occurs at an angle within the cross-section is the one that's going to cause this brittle material to fail. So we'll talk about how that looks, and that's basically the topic of the rest of this Chapter 9. All right, so first though, what are principal stresses? Well, basically those are the maximum and minimum normal stresses at a point. Usually it's going to be at a point of concern. We almost always look at it where we're going to have our largest stresses. So at that point of largest stress, we then have to do a stress transformation to find at what angle the largest stress is going to occur. And that's the basis for the setup for the derivation of principal stresses. So first, before we find the principal stresses, we're going to talk about how to find the angle at which those principal stresses are going to occur. In order to do that, we have to differentiate our transformed normal stress equation. That was our sigma x prime equation here from the previous set of lecture slides. And then if we set that differentiation equal to 0, this is what you get when you differentiate that equation for sigma x prime with respect to theta. Set that equal to 0, solve for our 2 theta, and you get this equation. This is tangent of 2 theta, and the p is standing for the angle at which the principal stresses occur, so that's theta p, is equal to our tau xy divided by sigma x minus sigma y divided by 2 in the denominator there. If you solve this equation for theta, you get 2 roots, theta p1 and theta p2. That's basically because you can have 2 possibilities for your inverse tangent due to the periodicity, that's a fun word, of tangent of theta. And if we're then dividing it by 2, we can use 2 periods of the tangent function to satisfy the equation. That's how you get 2 roots. We have 2 possibilities for theta that'll satisfy the equation. And that's shown here in this diagram. So the 2 theta p1 takes you to here. 2 theta p2 is just 180 degrees from 2 theta p1. But then what we're really doing is transforming our element by theta p1 and theta p2. So this original element with our sigma x, sigma y, tau xy becomes sigma 1 coming out of the x prime and sigma 2 coming out of the y prime faces. The angle from x to x prime is that theta p1 that we saw from here, and then the angle from x to y prime, where it's labeled x double prime here, is going to be theta p2. All right, so it's the angle from our original axis as our element was set up to our axis coming out of the faces where our principal stresses are acting. All right, so that's how you find the angles at which the principal stresses occur, just from this equation here. Now, what are those actual principal stresses? Well, all we have to do is plug back in that theta p1 and theta p2 that we found from the equation into our transformation equation, and we get this equation for our principal stresses. Sigma 1 and 2 are the average of sigma x and sigma y, so sigma x plus sigma y over 2, and then plus or minus the square root of this. So sigma 1 is going to be the one from the plus, sigma 2 is going to be the one from the minus. That's because sigma 1 is always greater than or equal to sigma 2. And again, these are our principal stresses. And on the previous slide, we found that the corresponding planes in which they act are the principal planes. Okay, we also saw on that last slide this same figure, but I want to note again that when our state of stress is represented by the principal stresses, no shear stress will act on the element. And you can also see this if you plug theta P1 and theta P2 into your shear stress transformation equation, that tau x prime y prime equation from the last set of slides, the one that I initially had a typo on but corrected the YouTube video. If you caught that, thank you. But anyway, you can always check your work with different equations. So that's another nice thing about these equations. All right. So in a similar fashion to what we did to find the angle for our principal stresses, we can do the same thing for our max in-plane shear stress. So we take the derivative of our tau x prime y prime equation with respect to theta, solve it for theta, and we get this very similar equation to our 2 theta p. So tangent of 2 theta s is equal to the negative of sigma x minus sigma y over 2 divided by tau xy. And if we go back, we'll see that's actually just the negative of the reciprocal of our tangent of 2 theta p equation. So our state of stress at the point where we have maximum in-plane shear stress is going to be at the root of this equation. So your angle from your x to your x prime axis is theta s1, and then a further 90 degrees is theta s2. To find your maximum in-plane shear stress, you just plug back in the theta s1 and theta s2 that you just found into your tau transformation equation, and you get this equation that you can use for your tau max in-plane stress. You can see it's plus or minus, basically tells us that you're going to have the same value for your max in-plane shear no matter what face you're on. It's just if you go 90 degrees, it's going to be the negative of the previous shear stress. So this is your equation. And again, if we go back a couple slides, it's the same as the radical we had to find your principal stresses. And we'll see what the implications of that mean in the next set of lecture slides. Right? And then also note that when we're at our max in-plane shear stress, we end up being at our average normal stress as defined by adding up sigma x and sigma y, those are your original normal stresses, before you transform and divide that by 2. So coming out of every face of our element when we're at a point where we have maximum in-plane shear stress is our average normal stress. So average normal stress there, 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 and there, all either tensile or compressive, just depends on what sigma x and sigma y were. Okay, so again, max in-plane shear on every face, just following the sign convention. You'll notice that on this and with any element that's transformed, or just any element in general, there's a pattern to your shear stress. And I know I've mentioned this several times before when drawing elements, but it's extremely important to kind of catch on to this pattern that your shear stresses going around an element are all going to be equal in order to satisfy the equilibrium of the stress element, but also they need to be in the proper direction. So if we have it going in the positive y direction here, this one on the positive y face needs to go in the positive x direction. And then on the opposite faces, they have to be in the opposite direction. So if it's going up here on the right, it needs to be going down on the left. If it's to the right on the top, I know this is rotated, but still sort of the top, it's going to be going in the opposite direction on the opposite face. Or you can think of it as the arrows always point to only 2 corners, and they're always opposite corners from each other. And that's it for the concepts for what you'll need for the first set of the Chapter 9 homework. And I'll go through the example problems at the end of these slides that I'll post in a video here a little bit later. So I'll see you there.